Alright, here are some example problems on beats and uncertainty. First problem. A stationary police officer uses her radar gun to determine the speed of a motorist which is moving away from her. The radio waves from the gun oscillate at 10.5 gigahertz. When the 10.5 gigahertz signal and the waves bouncing off of the car are added together, beating occurs at 2.23 kilohertz. How fast is the car moving? Okay, so the first thing we know is that the beats, right? The frequency of the beats is just the difference in the two frequencies. Alright, so we have the frequency of the radar gun and we have the waves coming back from the car. The car's moving away from the police officer, therefore the frequency is going to be Doppler shifted down. So the beat frequency will be the frequency of the radar gun minus the frequency of the Doppler shifted waves. Alright, so what is the frequency of the waves coming back from the car? You can kind of think of it this way if you want to. I have the waves that go out. When they hit the car, you can think of the car as being an observer, alright? The car is moving relative to the source, and so the waves are Doppler shifted. Now these are light waves, so we use the Doppler shift for light, which is the square root of 1 minus the difference between the relative velocity, I should say, of the observer and the source. Remember, there's only a difference velocity that matters for light, unlike Doppler shift for sound, for example. Alright, so that's just basically the speed of the car divided by the speed of light, divided by 1 plus the speed of the car times the speed of light. Alright? That's the frequency that someone in the car would measure, but now those waves are going to reflect off the car and go back. You can kind of think of it as if the car is measuring that frequency, then broadcasting that frequency back. But again, since those waves going from the car back to the police officer, they're going to be Doppler shifted as well, right? Because the car, it's broadcasting those waves, but it's moving relative to the police officer, so we get another Doppler shift of 1 minus VC over C over 1 plus velocity of the car over C. Alright? And I multiply those together, I can get rid of the square roots, and then I'll multiply by top and bottom by C just to make it look simpler, and I get C minus the velocity of the car divided by C plus the velocity of the car, and it's Doppler shifted down in frequency. Another way you could think about this is you could imagine that the car, it's reflecting the waves back. It's kind of like a mirror. So you might imagine this police officer is seeing herself in the mirror. That is essentially. So it's as if the waves are coming from a source that was moving. Alright? Okay. Now, let's take this. We have our Doppler shifted frequency. Now, I know the beat frequency. What I want to find is the frequency of the car. So I just plug this in. What I know is this beat frequency, delta F, and that's equal to F minus this thing, which is F, C minus VC over C plus VC. Alright, now, at this point, I know this, I know this, I know this, I know the speed of light. I just have to find the speed of the car. Alright, so it's just a bunch of algebra. So I'm going to skip that step and just tell you what you end up getting then is that the speed of the car is, and you can work this out yourself, 31.835 ... meters per second. Alright? There's the answer. I could have asked a similar question. I'm not going to actually work through this one, but here's a similar question, but using, instead of the Doppler shift of light, it would use the Doppler shift of sound waves. A bat is flying toward a window. It emits a sound at 47.2 kilohertz. The sound reflecting off the window beats with the outgoing sound at a rate of 820 hertz. How fast is the bat approaching the window? Assume that the speed of sound is 343 meters per second. Right? I'm not going to work this out all the way, but once again, what we're given is a beat rate, which is just the difference in the frequencies. Alright? In this case, the bat is approaching the window, therefore the Doppler shifted frequency will be higher, so this is just going to be F prime minus F. If we weren't sure, we could have just put absolute values over it, right? That's how the beating works. We take the difference, take the absolute value. Alright? And then just to find F prime, once again, the bat emits a sound, the window hears it, alright? It's as if the window hears it, and in the window's case, it's not, the window's not moving, but the bat is, so we have V minus the velocity of the source, which is the velocity of the bat, alright? But then the window sends that sound back, and now the bat acts as the observer, and it gets another Doppler shift, which is going to be V plus velocity of the bat. I'm sorry, there should be a V up here and a V up there. Anyway, So that's how you find the Doppler shifted frequency. Then you can go and you can find how fast the bat is moving. Again, I could think of the bat as kind of looking at its sound image in a mirror, right? The window's acting like a mirror for sound, and it looks to the bat like it's hearing the sound from another bat approaching it at that same velocity. Okay, here's our final problem on uncertainty. A pulse laser has a gain medium that can amplify light with wavelengths between 500 and 750 nanometers. What is the shortest pulse the laser could possibly emit? Well, this is uncertainty relationship, right? And our uncertainty relationship says delta omega, delta t has to be greater than or equal to 1/2, which means that delta t has to be greater than or equal to 1/2 delta omega. So if I can find the range of angular frequencies of light that the amplifier can amplify, I can find how short of a pulse, the minimum length of pulse you could possibly make with that laser. Alright, so I just need to find delta omega. Well, I know that light travels at the speed of light, but the speed of a wave is just one wavelength per period. Light travels one wavelength per period. 1 over a period is frequency. Alright, so the frequency of a wave for a given wavelength is just c over lambda, right? I just solved that for frequency, which means that the angular frequency is just 2 pi c over lambda. So that means light at 500 nanometers, alright, we'll call this lambda A, and I'll call this over here lambda B, right? Light at wavelength lambda A will oscillate with an angular frequency omega A, which is just 2 pi c over lambda A. And light at wavelength lambda B will oscillate with an angular frequency omega B, which is just 2 pi c over lambda B. Alright, so delta omega is just then 2 pi c times 1 over lambda A minus 1 over lambda B. Alright, now lambda A is smaller than B, so it looks like I've got something that's going to be positive. If I am ever worried, I can just take the absolute value, right? Because delta omega is an absolute value. It's a spread, right? Anyway, now I want to know what the shortest pulse is. So I just come and I plug that into here, and this is just 1 over 2 delta omega, so that's going to be 4 pi c 1 over lambda A minus 1 over lambda B, right? And you plug that all in, and it turns out that your answer, if you work this out, you should get 0.465 femtoseconds, or 0.465 times 10 to the minus 15 seconds.